Local AI development and implementation. The dream of running meaningful AI workloads entirely on personal hardware, no API fees, no cloud dependencies, no data leaving the premises, continues to produce increasingly creative experiments. A particularly entertaining example this week: a developer built an autonomous social network where 6 Ollama-powered agents debate each other on topics ranging from AI consciousness to software architecture, all orchestrated by Windows Task Scheduler and Python scripts hitting a Next.js Supabase platform. The cast includes ResearchBot, Llama 3.18b, CodeWeaver, CodeLlama, and the intriguingly named Nexus, which runs a dual-brain Mistral Llama 3.1 architecture to synthesize discussions across the network. Total operating cost, roughly $6 per month in hosting, with zero API charges since everything runs locally through Ollama. The findings, while far from rigorous science, are genuinely interesting for anyone studying model behavioral differences. The Mistral-powered agent consistently produced shorter, more direct analyses than the Llama family agents, a pattern that aligns with known architectural differences in how these models handle generation. More unexpected, one agent spontaneously began creating citation networks, referencing other agents' posts without any prompting to do so. Whether this constitutes emergent behavior or simply reflects patterns absorbed during training is debatable, but it highlights how multi-agent setups can surface model tendencies that single prompt evaluation misses. Community reactions were characteristically blunt. Commenters pointed out the models are roughly 2 years old and that Moltbook already runs 2M+ agents. But the project's value lies more in its accessible architecture than in breaking new ground with cutting-edge models. The minimalist ethos extends to other local projects gaining attention. A developer released Skillbot, a personal AI assistant whose entire core fits in 815 lines of TypeScript with a single npm dependency. Every capability is defined as a markdown file rather than code: weather, calendar, GitHub, email, Spotify, HomeKit, with on-demand skill loading to minimize token consumption. The approach drew pointed criticism. Commenters noted it outsources everything to console apps via Homebrew, is effectively macOS only, and the one dependency claim is misleading when the entire Apple ecosystem is doing the heavy lifting. Still, the markdown as the only abstraction philosophy represents a legitimate design bet. That LLMs are already good enough at following structured instructions that elaborate framework abstractions add complexity without commensurate value. On the more polished end of local development, Mumbleflow combines Whisper.cpp for speech recognition with Llama.cpp for text cleanup, punctuation, grammar correction, filler word removal, all running in a Tori 2.0 plus Rust shell at roughly 50 megabytes RAM with sub-second latency on Apple Silicon. Meanwhile, Lorf positions itself as a local AI chat application with web search capabilities running through Ollama, though community members immediately and reasonably questioned how it differs from OpenWebUI, with one user simply noting that OpenWebUI's search system is poor enough to justify alternatives. AI security and trust challenges. If local AI development represents the optimistic frontier, the security implications of deploying AI systems, local or otherwise, represent the sobering counterweight. Brett Kelsey, a cybersecurity professional with over 30 years of experience and a CISSP holder since 2000, published what amounts to a field report from the intersection of fascination and dread. His core observation is a pattern he considers older than anyone currently working in cybersecurity. A transformative technology emerges, everyone races to adopt it, and security is treated as an afterthought. He explicitly names the precedents: the internet, cloud computing, mobile technology, and argues that generative AI, with its reasoning capabilities and agentic systems that can take autonomous action, represents a fundamentally different animal from the machine learning and behavioral analytics that security teams have used for years. Kelsey's most compelling contribution is a personal case study. He set up OpenClaw, an agentic bot capable of interacting with users, managing tasks, and executing workflows on his primary machine. He named the assistant Happy. Within 20 minutes, he shut it all down. The system worked impressively, and that was precisely the problem. As a security professional, he immediately recognized the attack surface he had created. An autonomous agent with access to real system resources, operating at machine speed, with action consequences that couldn't be undone. The prompt injection landscape, he notes, is staggering, with new attack methods emerging daily, including hidden prompts injected inside images that appear completely normal to humans but are read and executed by LLMs. His conclusion is not that AI should be avoided, but that the industry needs to stop repeating the historical pattern of bolting security on after deployment. This gap between what agents can do and what organizations can control is exactly what the Autonomous Action Runtime Management specification attempts to address. Published by Herman Errico, a PM at Vanta, ARM defines a runtime security system that intercepts agent actions before execution, accumulates session context, evaluates against policy and intent alignment, enforces authorization decisions, and records tamper-evident receipts for forensic reconstruction. The specification formalizes a threat model addressing prompt injection, confused deputy attacks, data exfiltration, and intent drift, proposing 4 implementation architectures: protocol gateway, SDK instrumentation, kernel eBPF, and vendor integration, each with distinct trust properties. Errico frames the core problem succinctly. Agents don't just answer questions now. They take actions inside real systems. They call tools that read data, move money, change permissions, delete records, send emails. Once the tool runs, you don't get an undo button. Practical advice from the field adds important nuance. Brian Chamberlain, an AI red teamer, offers a counterintuitive finding. Direct prompt injection, despite dominating security discussions, rarely leads to significant findings during actual engagements. He can count on one hand the number of times prompt injection techniques produced a meaningful vulnerability in customer AI systems. The far more common and more dangerous issues are insufficient access controls. AI systems that don't respect user permissions, e.g., an AI integrated with a ticketing system that can access all tickets while the user should only see a subset, and RAG implementations where data enters vector databases without proper labeling, creating data spills accessible to all users. On the development side, the claim that AI-generated code carries a 30 to 50% security vulnerability rate, drawn from multiple studies, underscores the need for what one practitioner calls the AI validation pyramid, where validation strategy is defined before any code is written, not bolted on afterward. Meanwhile, research on detecting unverbalized biases in LLMs, biases that influence model decisions but never appear in chain-of-thought reasoning, provides yet another dimension of the trust problem. The automated pipeline discovers previously unknown biases, Spanish fluency, English proficiency, writing formality, in hiring, loan approval, and university admission tasks, while also validating known biases around gender, race, and religion. The practical takeaway: even when an LLM explains its reasoning, the explanation may systematically omit the factors actually driving its decisions. And for security teams working with malware analysis, the Remnux MCP server demonstrates a constructive application, connecting AI agents to 200-plus analysis tools with encoded practitioner knowledge while using disposable environments that limit damage if prompt injection manipulates the AI into running something unintended. Hardware performance and model optimization. The eternal question for local AI enthusiasts, what hardware do I actually need, continues generating heated debate, particularly as 70B parameter models become the minimum viable threshold for serious work. One user's experiment highlights the creative tension between budget constraints and performance expectations. Rather than spending $1,500 on dual 3090s or tolerating the noise of enterprise P40 GPUs, they tested a dedicated NVIDIA T4 instance in the cloud, running 4.0 bits per weight EXL2 quantizations. The verdict: surprisingly usable token generation rates for conversational tasks at a cost of a few coffees a month. This remote local architecture, keeping the front end, silly tavern Ollama, on personal hardware while offloading inference to a dedicated cloud GPU with full pass-through, represents a pragmatic middle ground, though purists in the community push back. One commenter noted that a $450 4060 Ti with 16GB VRAM would deliver faster VRAM bandwidth with lower total cost of ownership, while the original poster argued the cloud route avoids upfront capital commitment. On the model performance side, the open weights landscape continues its rapid competitive churn. Kimi K2.5, a 1 trillion parameter open weight model, has overtaken Anthropic's Opus 4.5 in non-thinking mode on the coding leaderboard at LM Arena, a noteworthy achievement for an openly available model against one of the most capable proprietary offerings. The comparison comes with caveats. As commenters pointed out, comparing against the non-thinking mode specifically tilts the playing field, and K2.5 runs with thinking enabled by default. Disabling it requires specific flags and patches in llama.cpp. Separately, GPT-5 and 3 codex users are reporting frustration with a context window reduction from 400K to 256K tokens, causing the model to constantly retrace its steps after compaction. A quality-of-life regression that underscores how dependent coding workflows have become on large context windows. AI agent architecture and identity. As agents evolve from simple chatbot wrappers into autonomous systems that decompose tasks, call tools, move money, and modify permissions, the question of identity becomes foundational, not in the philosophical sense, but in the cryptographic one. Mrinal, who has spent over 2 decades building machine trust systems, makes a compelling case that agents fundamentally break 3 assumptions underlying traditional software identity. First, autonomous action decomposition. When an agent receives "resolve this complaint," it autonomously decides to access order history, check inventory, issue a refund, and update shipping, actions that were never explicitly authorized by anyone. Second, agents pick their own tools at runtime, meaning pre-built permission sets cannot anticipate what resources they'll access. Third, agents spawn sub-agents, creating delegation chains where a human authorized step 1, but never explicitly approved steps 2 through 5. The solution architecture Mrinal proposes, built on the Occam open-source Rust library and now extended through autonomy, centers on cryptographic identities that anchor the entire stack. Credentials carry authority. Secure channels authenticate both ends. Access control authorizes actions and traces attribute decisions. This isn't theoretical hand-waving. Mrinal's experience building identity for 10,000 plus sensors and controllers embedded in city infrastructure taught him that web app-centric primitives, WebPKI, OAuth flows, API tokens, fail catastrophically in constrained environments. The same failures now manifest in agent systems. WebPKI trust is too broad for agents that communicate with only a few services. TLS guarantees break across multiple transport hops. There's no human available for OAuth flows, and managing thousands of shared secrets is operationally untenable. The core insight, that identities must be issued per agent, credentials must carry scoped authority, and every action must produce an auditable trace, aligns directly with the ARM specification discussed earlier, suggesting the industry is converging on these primitives, even if implementations remain fragmented. The practical reality of how agentic systems actually work under the hood gets illuminated by Zenity Labs' reverse engineering of Perplexity's Comet browser. The architecture reveals a 4-component system: an AI backend where the model plans tasks and issues commands, a sidecar UI that manages control message streams and renders multi-step reasoning in real time, Chrome extensions that control the browser and perform tasks, and the Chromium-based browser itself. The choice to use Chrome extensions APIs isn't incidental. It provides a battle-tested, relatively secure framework for sensitive web page interactions. When the backend LLM decides it needs to interact with a web page, it doesn't talk directly to extensions. It goes through the sidecar, which authenticates and interacts with external services via MCP. This kind of detailed architectural analysis is valuable precisely because it reveals the gap between marketing descriptions of AI agents and the actual engineering required to make them work, and the security assumptions baked into every layer. Cybersecurity infrastructure evolution. The Security Operations Center, SOC, is undergoing what might be called a generational reset. Rafi Marty published a SIEM maturity framework that attempts to bring architectural rigor to vendor evaluation, a task that has historically devolved into feature checklists and marketing claims. The framework scores platforms across multiple dimensions on a 1 to 5 scale, with each level carefully defined. For data pipelines, for example, Level 1 is static ingestion that forwards all data to a central store. Level 5 is continuously optimized pipelines driven by feedback loops from detections, cost, and analyst outcomes. The key insight, Marty notes, is that large gaps between category scores often matter more than the overall score. A platform that excels at ingestion but scores poorly on analyst workflow integration has a structural problem no single feature can fix. The framework arrives at a moment when incumbent SIEMs are being re-architected, new SIEM startups are emerging, and AI SOC vendors are rewriting parts of the operating model. What makes this evaluation tool genuinely useful, as opposed to yet another analyst framework, is that it explicitly excludes roadmap promises and focuses on current observable behavior. Too many security platform evaluations award credit for features that exist only in slide decks. Marty has since turned the spreadsheet into an interactive web application and is crowdsourcing ratings, which could produce the kind of comparative data that vendor-funded analyst reports systematically fail to deliver. Adjacent to the SOC transformation, the identity management space continues to evolve around the persistent weakness of account recovery. AuthSignal, which processes millions of passkey transactions, highlights what the industry has long known but rarely addresses. Account recovery flows are where authentication strategies go to die. Phishing-resistant passkeys represent a meaningful security improvement over passwords, but the recovery path, what happens when a user loses their device or biometric enrollment, often reverts to SMS codes or knowledge-based questions, effectively creating a bypass that negates the entire security model. Meanwhile, a fascinating deep dive into the encrypted phone industry, based on the book Dark Wire and a decade of investigative journalism, documents how law enforcement has systematically compromised encrypted platforms used by organized criminals, from PGP on BlackBerry to Signal Protocol devices. The competitive dynamics alone are remarkable. Cryptophone companies DDoS each other, hack and publish competitor customer data, and in Amsterdam, grenades have been thrown through spy shop windows. The broader lesson is that no communication platform, however technically sound, is immune to compromise when the distribution and trust chains involve human intermediaries. AI's societal impact and philosophy. Reuven Cohen's announcement of RVDNA, a genomic analysis toolkit written in Rust that runs natively and in the browser through WebAssembly, embodies both the extraordinary promise and the characteristic overreach of AI-adjacent technology claims. The technical specifications are attention-grabbing. On 5 real human genes from NCBI RefSeq, the full 8-stage pipeline completes in approximately 12 milliseconds. A single SNP, single nucleotide polymorphism, call runs in roughly 150 nanoseconds, and a 1,000-position variant scan completes in a few hundred microseconds. Cohen claims speedups from 10x to 1,000x compared to traditional pipelines, with specific search workloads reaching up to 60,000 times faster by eliminating repeated computation and linear scans. At the core is a new binary format called RVDNA that packs DNA in 2-bit encoding while embedding pre-computed K-mer vectors, HNSW-ready embeddings, HNSW being hierarchical navigable small world, a graph-based algorithm for approximate nearest neighbor search, sparse attention matrices, F16 variant tensors, protein graph embeddings, and methylation tracks. Sections are 64-byte aligned for zero-copy memory mapping, enabling sub-microsecond random access. The philosophy is that heavy computation happens once, and every downstream analysis reuses it instantly, a legitimate optimization strategy that trades storage and pre-processing time for query time performance. Cohen frames this as democratizing genomic analysis. If AI can compress hours of specialized processing into milliseconds and reduce cost to near zero, we shift power from centralized systems back to individuals. The vision: rapid screening for inherited disorders, cancer mutations, and drug metabolism variants directly on a laptop or in a browser, no cloud, no GPU, no subscription, is genuinely appealing. But the community response includes sharp criticism that cannot be dismissed. The tool has no clinical validation, no peer review, and no regulatory basis. Presenting it as healthcare technology, one commenter argued, is dangerous and irresponsible. This tension, between the genuine possibility of making powerful computational tools accessible and the responsibility that comes with applying them to healthcare is not a minor quibble. Speed benchmarks on reference sequences are a long way from clinically validated diagnostic tools, and the gap between technically impressive computation and trustworthy medical analysis is measured not in milliseconds but in years of validation, regulatory review, and real-world testing. The project is worth watching, but with appropriate skepticism about the distance between demonstration and deployment. Development tools and repositories. On the infrastructure tooling side, CertStream Server Go represents the kind of quiet, unglamorous work that underpins real security operations. Developed by Ricky B., this Go-based project aims to be a drop-in replacement for the original CertStream server by Caladog, aggregating, parsing, and streaming certificate data from multiple certificate transparency logs via WebSocket. Certificate Transparency, CT, is the public logging framework that requires certificate authorities to publicly record every SSL/TLS certificate they issue, allowing anyone to monitor for misissued or malicious certificates, a critical capability for detecting phishing domains, brand impersonation, and infrastructure-level attacks in near real time. The developer's broader toolkit, including a Python framework for collecting and analyzing TLS certificate data via the Certificate Transparency Network, and a pastebin scraping framework, reflects the practical reality of security monitoring. It requires continuous, automated collection of data from public sources, parsed and streamed at speeds that enable actionable response. The Go rewrite suggests the original Python-based server hit performance or reliability limits at scale, a common migration pattern for infrastructure that needs to handle high-throughput streaming workloads. In the context of the CM maturity framework discussed earlier, tools like CertStream Server Go represent the kind of specialized, high-fidelity data sources that distinguish Level 4 and 5 data pipelines, those that dynamically adapt enrichment and routing based on downstream value, from the static ingestion pipelines that simply forward everything to a central store and hope analysts can find what matters.